Hello everyone, a very warm welcome to Code Magic Infinity, and today we are going to solve Leetcode 108. It's a easy problem. It's converting a sorted array to a binary search tree. So without any further ado, let's jump right to it. We are given an integer array nums where the elements are sorted in an ascending order, and we are required to convert it to a height balanced binary search tree. And they have also told us that what is a height balanced binary tree? It's basically a tree in which the depth of the two subtrees of every node will not differ by more than one. Okay. And they have given us certain sample cases to sort of explain what the output is expected to look like. Okay, so before we begin solving the problem, discussing the algorithm to solve the problem, let's actually understand what a binary search tree is. Okay, so I think many of you might already be aware. To those who are not aware, this will be a quick refresher or a quick glance into what a BST is supposed to look like. So basically, if you have root, left, and right, the idea of BST is that all the elements to the left of the root are going to be smaller than the root, and all the elements to the right of the root are going to be greater than the root. And of course, both the left and the right subtrees are supposed to be BST themselves. So for example, if I have 2 and if I have 1 and I have 3 here, then this is a BST. Okay, I can even make this 0 here, I can make this 4 here. So 1 itself is a BST, 3 itself is a BST. Okay, so just wanted to provide a quick refresher or a quick insight into what a BST is. Now with that out of the way, let's actually begin solving the question. Okay, so let's consider this sample. We have -10, -3, -10, we have -3, we have 0, we have 5, and I think we have 9. Okay, we are given this array and we are supposed to convert it into a BST. Now, as a naive approach, what might come into your mind is that I know how to construct a BST, I know the logic of it, so why not I go element by element, and as and when I encounter or I visit those elements, based on the BST logic, I place them in my binary search tree. So for example, first I encounter -10, so I'll make it as my root. Then I encounter -3. So I know -3 is greater than -10, so it will become a part of the right subtree. Then I encounter 0. So 0 is greater than -10, it's greater than -3. So it will become the right child of 3. Then I encounter 5. So greater than -10, greater than -3, greater than 0. It will become the right child of 0, and similarly 9, which is greater than all the elements encountered so far, it will become the right child of 5. So while this is a valid BST, okay, we have followed the logic, but as you can see, it's not a height balanced BST, which is also a requirement of our problem at hand, right? The height here of the right subtree is 5 and the height here of the left subtree is 0, right? So it becomes apparent that while this approach does give us a valid BST, it does not give us a height balanced BST. And the same thing would happen if you were to go through the string in the reverse order. Like if you were to make 9 as your root, and then you'll encounter 5, which will become the left child, you'll encounter 0, you'll encounter -3. So now all the elements will be in your left subtree, again, not giving you a height balanced BST. So, okay, so now we have figured out that maybe in a naive way, this is how it can be done, but it's not giving me a valid BST. So what else can I do to get a valid BST, or to get a height balanced valid BST? Okay, so we know we can't really begin from the first element and then take the BST. Similarly, we know we can't begin from the last element either and go from there to build a BST. How about we begin from the middle element? Okay, so let's say 0 becomes the root of your tree. Okay, now you know all the elements to the left of 0 are going to constitute your left subtree. So let me add -10 and -3 here. Okay. And I know all the elements to the right of 0. Because they are greater than 0, they will constitute my right subtree. Okay. So 5, 9 will come here. So basically what we have done is we have met the condition of a valid BST, and at the root level, I'm sorted. I am clear as to what will make my left subtree and what will make my right subtree. And the final condition of BST, as we discussed, was that the left subtree itself should be a BST and the right subtree itself should be a BST. So what I did on root, I can recursively keep doing it on my left and the right subtree to eventually get a full-blown BST, which will actually be our answer. So basically, I can, for example, if I consider -10 to be my root or to be my middle element, okay, on my left subtree, then I know that all the elements to the right of it are going to be the elements which make up my right subtree. Similarly, here if I consider 5 to be the middle element and I make it as my root, then I know all the elements to the right of it are going to make my right subtree. So all I did was I kept recursively applying the logic which I had discovered, and I ended up getting a height balanced valid BST. So at every step, we basically calculate a mid. Okay, mid is nothing but if this is my L or my left and this is my R or my right. So M is nothing but, or M or mid is nothing but L plus R by 2. Okay. So at every step, I calculated the mid, and then I said that, okay, from L to M minus 1, these will be the elements which make up my left subtree now. And from M plus 1 to R, these will be the elements which make up my right subtree. And I did the same thing again and again on my left and the right subtrees until, of course, there are no more elements left in the array. So I hope this drawing explanation makes things very clear. Although it's a simple problem, I think right from the basics, if we try to visualize things till the very basic level, it really helps us when we move on to the complex problems as well. And that's why I wanted to sort of draw it out, really get into what exactly is a BST, right? And then see that what could be the naive approach to do this? How do we optimize it? So take it step by step, basically. And of course, I think as most of you might have noticed, this is very similar to how we actually do binary search, right? In binary search also, we calculate the middle. And if we are looking for an element called as target, and if the target is lesser than the middle, then we search in the L to M minus 1 array. And if our target is greater than the middle, then we search in the M plus 1 to R array. So the logic is very, very similar, right, to binary search. And yeah, I hope this drawing explanation is clear. And the code is actually very simple. So let's quickly jump into it. I use Python 3, so I'll write the code in Python 3. And I'll also upload it on the GitHub link, which you'll find down below in the description. You can always navigate to it and yeah, have a look at the code as and when you want. So what I'm actually going to do is I'm going to create a helper function. So let's call it create BST of, okay. It will take the left and the right, which we were talking about, right? Initially, that left and right value is going to be 0 and length of nums -1 and nums as an argument, okay. And what does this function actually do? So let's create BST of, let's call it L, R, and nums as we discussed in our diagram. And we can say that as long as L is less than or equal to R, okay, till then we can keep sort of working with the array which we have. Okay, so if L is less than or equal to R, I can first make my root node. So I'll call it tree node of nums of mid. Okay, so mid is nothing but L plus R by 2. Okay, and then I need to create my left and the right subtrees. So for root dot left equal to We just need to invoke this create BST function for the left subtree as well. And for left, it is going to be L comma mid minus 1, and you need to send the same nums array again. And the right subtree will be equal to self dot create BST of mid plus 1 to R. Uh, there we go. And we send the same nums array again. And finally, we return root. If L is not less than or equal to R, we can just return none. So this should do it. Let's see whether it works or not. Yeah. Looks like I did a small mistake. Yep, there should be self here. Perfect. Let's try submitting it. And it is accepted. So there we go. We have solved the problem. Thank you so much for watching the video. Do like the video if you were able to follow through, and do subscribe to the channel as well. Thanks a lot. See you next time. Bye.